Hello and welcome back to Introductory Astronomy. Now we've talked about stellar birth and stellar evolution. How about stellar death? What fate awaits a star when it runs out of fuel? For a low-mass star, the white dwarf stage is not necessarily the end of the road. There is a potential for further violent activity if it has a binary companion that can provide additional fuel. High-mass stars, whether they are or not members of binaries, are destined to die explosively, releasing vast amounts of energy, creating many heavy elements, and scattering the debris throughout interstellar space. Right here you see the picture of the Crab Nebula, which is the debris field of a massive star that was seen in the sky about 1,000 years ago as it blew itself up to smithereens. Supernovae have been observed in many locations across the sky, often in galaxies far from our own. In this chapter, we're going to talk about life after death for white dwarfs, the end of a high-mass stars, a particular supernova called 1987A, the formation of the elements, and the cycle of stellar evolution. And let's start by talking about novae. A nova is a star that suddenly increases enormously in brightness, then slowly fades back to its original luminosity. Novae are the result of explosions on the surfaces of faint white dwarf stars caused by matter falling onto their surfaces from the atmosphere of larger binary companions. In frame C, we see Nova Hercules 1934, as it was in March 1935, so before it underwent the explosion, and in frame B, in May of 1935, after it brightened by a factor of 60,000. Frame C shows the light curve of a typical nova. A light curve is a plot of luminosity or brightness versus time. In this case, we have luminosity in our familiar solar units versus time in days. As you can see, we have a rapid rise in luminosity and a slow decline. The maximum brightness attained is very, very high. In this case, it's about 10,000 times more than it was before. The theory and observation are in good agreement on what takes place when we have a nuclear flash on a white dwarf's surface. So let's take a look at this a little bit more closely. If we have the scenario of a white dwarf in a semi-detached binary system, and these two stars are close enough, in this particular case we have a main sequence star, then the gravitational field can tear matter from the companion surface. So in this case, matter does not fall directly onto the white dwarf surface, but instead it forms an accretion disk of gas spiraling down onto the dwarf. And here is an artist's conception of a nova explosion. In frame A, you can see the white dwarf star, which is on the faraway upper left, as it orbits a cool red giant. As the dwarf swings around in an elliptical orbit, it comes closer to the giant. Once that happens, material begins to accrete from the giant to the dwarf and begins to accumulate on the white dwarf surface, as seen in frames B and C. The dwarf star eventually ignites in hydrogen fusion as a nova outburst, shown in frame D. Here we have the matter ejection from a nova. This is nova Persei, taken about 50 years after it suddenly brightened by a factor of 40,000 in 1901. This photograph corresponds approximately to the artist's rendition of frame D in the previous slide. So let me go back for a second here. So frame D right there corresponds to a photograph in frame A over here. Here we have photographs of nova Cygni as were imaged by the Hubble Space Telescope in its eruption in 1992. In the left, we see a picture of more than a year after the blast, and you can see the billowing bubble of ejected material. At the right is 7 months after that, and you can see how the shell is continuing to expand and distort. These particular images are fuzzy because our object is more than 10,000 light years away. What happens at the end of a high-mass star? A high-mass star continues to fuse elements, heavier and heavier elements, until it gets to iron. As heavier elements are fused, the reactions go faster, and each stage is over more quickly. For example, a 20 solar mass star will burn carbon for only 10,000 years, but its iron core lasts less than a day. Here we have a cutaway diagram of the interior of a highly evolved star of mass greater than 8 solar masses. Notice how the interior resembles the layers of an onion, with shells of progressively heavier elements burning at smaller and smaller radii and at higher and higher temperatures, all the way up to iron. This graph here shows the relative stability of nuclei. On the left, nuclei gain energy through fusion. And remember, fusion is the combination of elements to form heavier elements. On the right, we see that they gain energy through fission. Fission is the opposite of fusion, is the splitting up of elements into lighter elements. Iron is very important because it is the crossing point. When the core has fused to iron, no more fusion can take place. If we take a closer look at the graph, we see how the masses per nuclear particle, proton or neutron, of most nuclei vary with nuclear mass. We see information about nuclear structure and stability. When light nuclei fuse, the left side of the graph, the mass per particle decreases and energy is released. When heavy nuclei split apart, the right side of the graph, the total mass again decreases and energy is again released. The nucleus with the smallest mass per nuclear particle, meaning the most stable element, is iron. It can neither be fused nor split to release energy. The difference in mass between a given nucleus and the value for hydrogen represents the amount of mass lost or energy released if free neutrons and protons were combined to form that nucleus, or equivalently, the amount of energy needed to split the nucleus into its component particles. The inward pressure in these scenarios is enormous due to the high mass of the star. There is nothing stopping the star from collapsing further, and it will do so very rapidly in a giant implosion. As it continues to become more and more dense, the protons and electrons actually fuse with each other and become neutrons and neutrinos. As you know, neutrinos can pretty much go through anything, so they escape. So what we're left with is neutrons, which are compressed together until the whole star has a density of an atomic nucleus, which is about 10 to the 15 kilograms per meters cubed. The collapse will continue. It will compress the neutrons further and further until there is a recoil in an enormous explosion known as a supernova. In the picture right here, we have SN 1987A. SN stands for supernova and A for the first supernova observed in that year. And you can see that in the right frame on the arrow point. It exploded near a nebula called 30 Doradus. The photograph on the left is the normal appearance of the star field before the supernova explosion. Now, supernova is incredibly luminous. If you look at these light curves here, it can be 1,000,000 times as bright as a nova. Here we see type 1 and type 2 supernovae and their typical light curves. In both cases, the maximum luminosity can reach that of 1 billion suns. But there are characteristic differences in the fall-off of the luminosity after the initial peak. Type 1 light curves somewhat resemble those of novae, but the total release of energy is much larger. Type 2 curves have a characteristic plateau during the declining phase. Now, a supernova is a one-time event. Once it happens, there is little or nothing left of the progenitor star. Type 1 supernova is a carbon detonation supernova. It results when the white dwarf in a binary system has exceeded what we call the Chandrasekhar mass limit. That is a mass limit of 1.4 solar masses. So during the accretion of mass from its companion, if the white dwarf reaches 1.4 solar masses, it will undergo a carbon detonation supernova, and the resulting spectrum will contain no hydrogen lines. A type 2 supernova, on the other hand, is the death of a high-mass star that has developed an iron core. Carbon detonation supernova, in a little bit more detail, we need to have a white dwarf in a binary star system. If the white dwarf's mass exceeds 1.4 solar masses, what happens within the white dwarf? Electron degeneracy can no longer keep the core from collapsing. Carbon fusion starts throughout the star almost simultaneously, which is what results in the carbon explosion, and therefore a carbon detonation supernova. Here is the artist's renditions of the schematic, the evolutionary history of each type of supernovae. In frame A, we see that a type 1 supernova usually results when a carbon-rich white dwarf pulls matter onto itself from a nearby red giant or main sequence companion. In frame B, we see that a type 2 supernova occurs when the core of a high-mass star collapses and then rebounds in a catastrophic explosion. Here we see the remnant of an ancient type 2 supernova called the Crab Nebula, or M1. It resides about 1800 parsecs from the Earth and has an angular diameter of about 1/5 that of the full moon. Its debris scattered over a region of about 2 parsecs. In 1054 AD, Chinese astronomers observed this supernova explosion. The main image shown here was taken with a very large telescope in Chile and the inset by the Hubble telescope in orbit. Now, the velocities of the material in the Crab Nebula can be extrapolated back using Doppler shifts in order to find the original place of the explosion. Right here we see positive and negative photographs of the Crab Nebula taken 14 years apart. See how they do not exactly superimpose, which indicates that the gaseous filaments are still moving away from the site of the explosion. The positive image in glowing white was taken first, and then the black negative filaments were overlaid later. Hence the black but still glowing debris is further from the center of the blast. This is the Vela supernova remnant. Extrapolation shows that it exploded about 9000 BC. These remnants are spread across 6 degrees of the sky. The inset shows more clearly some of the details of the nebula's extensive filamentary structure. If you look closely, you see a long diagonal streak, which was caused by the passage of an Earth-orbiting satellite while the photo was being exposed. Your book talks a little bit about supernova 1987A. It occurred in the Large Magellanic Cloud, and it was the result of a 15 solar mass type B supergiant exploding. And you see right there the associated light curve. In general, supernovae should take place about 1 or 2 every 100 years. There hasn't been one in our galaxy for about 400 years, so we are a little bit overdue. Now, there's a couple of things that make this supernova very interesting, and I would direct you in the book to see what those are. But these images right here show how core debris, represented in purple, is moving outwards toward the ring. The 6 insets show material cooling and becoming fainter as the remnant expands at nearly 3,000 kilometers per second. The main image reveals 2 additional faint rings that may have been caused by radiation sweeping across an hourglass-shaped bubble of gas. That gas could have been the result of a non-spherical bipolar stellar wind from the progenitor star before the supernova occurred. So study chapter 21.1 through 21.3. Be able to explain how white dwarfs in binary star systems can become explosively active. Be able to summarize the sequence of events leading to the violent death of a massive star, and describe the 2 types of supernovae and explain how each is produced. Until next time.